questions yesterday, I'm happy to clarify anything. Surprise, surprise, primary presidential vote. And here's the grid. So one nice thing about GBM is that it's a little bit simpler. So we start, when we start getting into XGBoost and things like that, more powerful, you have more hyperparameters, but that's a mixed bag, right? That adds complexity. Here, we have more hyperparameters than we do for random forest, and those will be more consequential, but it's more manageable. It is only 4, so a little bit easier to deal with. So let's go through those. N-tree, that's capital B, right? The number of boosting iterations, or of course here, the number of trees that are being estimated. I'm cycling through 102,000, so right, this is just 1 through 20. Each of those are multiplied by 100, so we're just getting sequences of 100, 200, 300, 400, 100 at a time. So I'm going to try out these, world where I fit 100 trees, I fit 200 trees, I fit 300 trees, and see how those differ in terms of performance. This interaction depth is the lowercase d from the slides. How deep do we allow the trees to be? With the important consideration that this is also going to be equivalent to the maximum order of the interaction that we allow. If we only allow a tree, individual trees of depth 2, that's not going to be able to fit any 3-way interactions. It's going to be able to fit up to 2-way interactions, and then up to more generally D number of, D where D is depth, number of interactions, or order of interactions, I should say. So we try out a bunch of values there, see what pops. Shrinkage, these are 2 good values. Of course, we could go even smaller. That probably is overkill, but it's not, certainly not a bad idea to play around, just usually not necessary. So I'm just going to try 0.01 and 0.05, mainly to make a point about what happens, and it'll be pretty clear when we run this. So yeah, certainly for starting out, I feel like this is these are 2 good ones to throw in. They're usually pretty safe, and of course it'll all adjust depending on the number of trees. When we run this, we're going to need more trees. When we run this, we're going to need fewer trees. But this one may be, in fact, certainly will be, it'll get the process of overfitting more quickly. This is going to move, 5 times as slow when it's fitting the trees and attacking those residuals. Number of minimum observations in node. We've called this bucket. We've called it minimum node size. GBM has this particular term for it. Right, it's the number of observations that are allowed in the final leaves of the tree. Right at the very bottom, we need to be able to populate at least 5 observations in each of those nodes. So a little bit of an additional guard against overfitting. I just made this, I set this at 5 to give us, to make these a little bit quicker. Of course, we could, just like with random forest, and probably should, try out some different values, but whatever, for here, just for speed, purposes of speed, I'm going to run this. And let me get it running, so I'm waiting for it. Start to see this gets a little bit slower, still sort of manageable, but things do start to get a little bit slower. We're trying that many more combinations, and also the methods themselves are getting increasingly complex. It ran fine, so it's we had to wait hours and hours, but things are going to start to slow down. The only other thing to mention here that's different is this bag dot fraction. That is not a coincidence. Bagging, right? This bootstrap aggregating. This is the stochastic part. This is saying that when it's 0.5, that we're taking a random subsample of proportion equal to that at each step of the process. So this is saying take a random proportion of 0.5 or take a random half of observations, create that bag, that bootstrap aggregate, or excuse me, just the bootstrap replicate, I really should say, of observations at each time. You could set this equal to 1, and it would be non-stochastic GBM, With XGBoost, I think one nice thing about XGBoost is this is set as a tuning parameter that we can play around with. We can try 0.5, we can try 1, we can try 0.1, any value between 0 and 1, greater than 0, of course, will work there. Here we have to hardwire it. I found, for whatever it's worth, not an exhaustive survey, but I think I've always found, or certainly more times than not found, stochastic is a better way to go. And the default value there is 0.5. Now, is 0.5 better than 0.6 or 0.4? I don't know. I really need to tune that to find out. We are here starting to operate really at the margins, where, you know, it's like we want the better model, but do we really want to go through the hassle and expense to get that better model when what we mean by better is that much improvement? Maybe, depending on what the incentives are. But I don't think this is something that should keep you up at night too much if you were to set this at 0.5 or any reasonable value. Now, if it's something you want to tune and play around with, great, that's wonderful. XGBoost is probably a better way, but XGBoost is more complicated. It's more time to spin. So that trade-off is certainly present here. I always set these things to 0.5 and find that they work well. But setting it to 1, we're going to get very similar performance. So whatever. I like to set it to 0.5. I think that's a good general goal. Stochastic GBM was a real step forward in the world of boosting, and I tend to think that that's usually both a theoretical improvement, a more theoretically valid way, and empirically, more often than not, leads to slightly different, a slightly better performance. Okay, so let's look at the result. So the biggest thing is that on the x-axis, pull this up. We have number of trees, or number of boosting iterations, whatever you want to call it. So, and on the y-axis we have area under the RLC curve. So we want higher values. Higher values are better here. When shrinkage is set, or that learning rate is set to 0.05, so it's moving faster than the 0.01, we start dropping off essentially immediately. The blue does jump up and then it starts to drop down. This is probably too great, almost certainly too large of a learning parameter. Right? I'd like to see something much more like 0.01 where this is underfitting, right? We're moving slow. Kind of think of this slide, if you would. You know, that when we only do 100, 200, 300, we're making improvements, but it's going to take a little bit longer. Here, we're almost jumping over this, when it's 0.05, we're making that jump such that overfitting starts really out of the gates. Not severe overfitting, but we get worse and worse and worse estimates of performance the more and more trees that we fit. Here, going from 100 to 200 to 300 to 400 to 500, some number of trees, depending on D, the maximum tree depth, we definitely get improvement. Right, so we've explored some configurations where we're almost certainly underfitting over here, and then we start to see it trail off slowly, but it is trailing off, overfitting over here. And it looks like a sweet spot is going to be, let's see what exactly it is for me, 900, that's usually right. So this blue point right here, maximum tree depth of 2, looks like that's going to be a good choice, where I've tried values lower than that, right? I've tried fewer trees, I've tried more trees. This one gives me the best. It's really close, but again, if I have faith in the cross-validation process, I should choose the best configuration, and that's one that does, it makes a reasonable sense that you would have about 900 or 1,000 trees, where we have a learning rate that's small, but not ridiculously small. If we went back and tried, 0.1, something like this, or then on the other hand, 0.1, It's just going to be more extreme versions, of course, of what we see, what we saw with these particular results, that this is going to take, with 0.001, it's going to take even longer, which, okay, that might be worth it. On the other hand, if we set to 0.1, like, that's going to, 0.1 is definitely going to be too high. So, yeah, 0.01, I find that that's a good kind of general guideline. And the nice thing is that it's, for any given learning rate, you can always, if you can just run enough trees, you can find a good configuration for it, or at least a reasonable configuration for it. It's just with shrinkage of something like 0.05, I would have to limit it to only 100 trees. It's okay, I guess, but really, I'd like, I'd like more than that. 100 is a wee bit on the small side. I have more faith in getting a low variance estimator when we build it using 900 trees with a slower learning rate. Cool. So, this ran, life looks good. We can, as usual, extract, because we have that holdout testing set, we can look at how we performed training and testing. We're going to focus on the area under the curve, 9.7, 9.5. This is a good model. It's about what we got with random forest, although note that random forest in sample was like 0.9914, like almost perfect, which good, but overfitting was a little bit of an issue because the out of sample RLC there was like 0.94, 0.95, something like this. Might even have been 0.96, so it may still have beat it. Random forests are prone to overfitting, or at least slightly overfitting, because really you would also need to tune the number of trees as well. More fundamentally, it ends up being that setting the residual as the target, or that updated vector of residuals, is actually kind of surprisingly more effective, right? It actually is more of a constraint in guarding against overfitting and forcing trees to become different and to look different than are the random forest, because with random forest you have this fundamental issue of, okay, wants to keep going back to Mexico wall, it wants to use that again and again and again and again. It's only going to be able to do that some set of times, but anytime something is paired with Mexico wall, it's going to be used. So Mexico wall is going to be used a ton in random forest. It's going to be used a ton here as well. But it's going to be able to adjust based on how effectively going back or not to Mexico wall is in attacking that updated vector of residuals versus a random forest where we're not worried about the, we're going back to the original data. We're going back to fitting Y. And so it's not a huge distinction, but it is a little bit more, also a selling point for boosting, that random forest, not crazy that you would end up with a perfect fit in sample and, an area under the RLC curve like 0.89 or 0.9, which is evidence of some overfitting. I don't think it's disastrous. I mean, there's obviously no good thresholds for what is an acceptable amount of overfitting, an unacceptable amount, but certainly the greater the divergence between the training and testing performance, it means that overfitting is more and more of a concern. So the idea that the training fits better than the testing, that's almost always going to be true. But is it close? And here it's definitely close. With the random forest, it's probably sufficiently close. I don't think anyone would make a huge deal about it. But to the extent that that does concern you, it seems like it's a pretty strong regularity that boosting does a properly tuned boosting models is more effective at preventing overfitting than random forest. But whether or not that's even an issue in the first place, very, very data dependent. It's just something that can and does pop up. Yeah.
Could you elaborate on which part of the data the fitting starts with boosting? Because I feel like for a random forest, it's like there's more certainty with like just a random selection of predictors. And then, like in the figure you shown on the slides, it seems like the learning starts with the center of the data and then gradually expand.
So it starts out fitting the, just the Y. So, like, with boosting, it's gonna start out, the same as just a single decision tree. So it's gonna use all the, it'll have all the predictor variables and it'll have the Y. And if we do stochastic, it'll just use a random, subset of observations. But after that, it's going to be that updated version of the residual to say, okay, now I have predictions from that tree that I just fit. Here's are the remaining residuals. Actually, I'll come up with new predictions for that, and then I'll update the vector of residuals each time. So it starts out, the very first iteration of this is just that the residuals that we fit are equal to Y initially. We initialize what we're fitting as Y, which is exactly the same as when we fit a single decision tree. What happens after step one is where things get interesting, where we update the predictions and then we update the residuals from that, and then we fit a new tree to that R sub I, which is each time a combination of what are the existing residuals and what are the updated predictions of the boosting model at each step. So that's we're still, while we're not constraining the predictor variables here, although we actually can do that next GBoost, but with basic boosting here, we're not making any of those kinds of controls. What we are controlling is the proportion of observations that are being used to do these calculations, to fit the trees and then to do the updating. And the key, the most important part is that what we're fitting is R. The vector of residuals, R sub I for all the I 1 through N observations, that initially is equal to Y, but after that it is an updated version where you take, what is Y minus Y hat, or a shrunken version of Y hat? What is the predictions that are that are different from Y, and that'll be the new residual, and we just keep repeating that process, however many iterations.
I see. I was just thinking, the residuals for each iteration might not be the same, or like it might not improve every time with like the lambda thing. But I feel like in the code, it shows like the learning is pretty smooth and it's like keep.
Yeah, good point. Yeah, no, it's good. It's a good question. It's and that's one of those things. I have to go back and look at that through the boosting book. If it's I don't know if there are consistency guarantees that sort of law of large numbers that any given tree might not produce an out of sample improvement, but that becomes more and more likely the more trees that you're adding. So, if we went through this, I just do them in batches of 100. And what's weird about boosting is that there even would be any kind of theoretical or asymptotic guarantees anyway, but boosting is kind of weird. It's kind of this hybrid between maximum likelihood methods where there is more theory and then machine learning algorithms where there is, of course, much less theory. So there may even be a proof that we could derive and show that that's going to be true in the limit, that as the number, as these batches are larger and larger, your probability of improving is goes to 1, goes to complete surety. I don't know whether that's a theoretical guarantee or not, but either way, it's definitely an empirical regularity that you're right. Any given tree, so if I did that and I just went 1 tree, 2, 3. Examine them one at a time. That may or may not occur. Over larger values, though, it's almost certain that you're going to do a better job of improving, and then at some point you don't. Right? That's it's not super, super dramatic here, but, well, it's more dramatic with the 0.05. Right, that we're adding more trees and we're getting worse and worse because we've saturated the algorithm. We're now fitting irreducible error because we are attacking the residuals too aggressively in terms of any given tree, and also in terms of the overall number of trees. So we're attacking the problem too hard, and we're punching it too many times. Some combination of both of those things here. This is obviously going to be smoother because, right, it is moving a very little bit at a time, and for any one of these trees, you kind of see, there's like a real clear, but sometimes things will kind of pop up and pop down. Certainly, if you made this more resolution, but what happens is that tends to get smoothed out empirically, and again, possibly theoretically, but definitely empirically when we, are looking at it, when we zoom out a bit and start looking at it in terms of batches of large numbers of these iterations that we're throwing at it.
Yeah, because I see like we have 4 in total hyperparameters here, so I would envision like more instability.
Yes, which is why that learning rate is so great that like we allow, it's kind of interesting here that when we have too few trees, it's most preferring that tree of depth 4, right? It's just, this is underfeeding, and so it's so thankful to have the ability to grow more complex trees. It's doing better by being able to grow more complex, deeper trees. That inflects, right at some point right around here, where now we're moving into the world of overfitting, and it prefers the max tree of depth 2. And so now we do worse by adding more complex trees. So, and also, right, like there's a little bit shakier, right? I don't want to make too big of a deal of that, but what's great about that learning rate, having that learning rate small, is that it's moving in the right direction. It is improving, but it's improving slowly, and that helps to prevent the stability issues that accrue from the fact that, right, we're simultaneously, exactly like you say, testing maximal tree depth, and we're trying to, here I just set minimum observations in node to 5, but we could try that as well. So there's a lot of things going on. But if that learning rate is sufficiently small, it's not able to be that radical. It's going to take a lot of iterations to get a large improvement, and by the time we've done a large number of iterations, well, as we've already seen, miracle of aggregation, combining a bunch of these trees together, even if the individual trees are high variance, that tends to cancel each other out the more trees that we add. Those are actually quite stable, in part because they are high variance, they're diverse, and combining them tends to prevent any single tree or type of tree from dominating the ensemble.
Do you have any suggestions as to how we should navigate these unknown hyperparameters?
Yeah, I think going back and testing, for me, I'm pretty satisfied with it because I've seen, the biggest thing for me is I want to see areas where we've done worse on the underfitting side and areas that we've done worse in the overfitting side, and we have that here, right? And so my optimal value is 900. I've tried values less than 900, I've tried values more than 900. So this is pretty good. Now, we can always go back and add to this. We could play around with different, expanding the choices on any one of these hyperparameters, going back and trying a very, very small shrinkage parameter. You're unlikely, this is again where we're starting to get into really marginal differences that I'm pretty confident that none of these is going to, I don't doubt you could get a configuration that's better than the one that I found, which is 900, whatever it was. Yeah, this particular one. You probably do a little bit better than that, but I just doubt you're going to get that much of a difference because, first of all, this is just a reasonable parameter, like the shrinkage parameter of 0.01, that's usually a nice choice. Then you don't have to choose that, but that usually is a nice one. And I've been able to see combinations of number of boosting iterations that do worse on one end and do worse on the other. I could hone in if I wanted to and really, should this be 824, should it be 873, should it be 926? I could get down to that level of granularity if I wanted to, but now we're talking about, just really minimal improvements in fit. Maybe worth it, depending on what your incentives are. Usually the big picture, right, is just not going to make an enormous difference in the what you can glean from the model. The only thing you maybe could glean from the model is a little bit of an extra bump in terms of performance. But yeah, I mean, if you're seeing both ends of this, I mean, this is really a painted out version, a pretty nicely painted out version of the classic. Should really just have this at beck and call at any time. This, now here, we're trying to minimize it in this classic slide. In the R code with GBM, we're trying to maximize it, we're trying to maximize RLC, so just think about flipping that around. But yeah, this is what we see, right, is down here on this bottom panel. For 0.01, we get to see that inflection point. And there it is, and so I'm pretty comfortable that that's a good way to go, although, you know, talked about a little bit yesterday, can always go back, never a bad idea to go back and try different kinds of parameters. Maybe I want to do this, maybe I want to, you know, especially if like it's giving me the answer of 2, maybe I even want to try 1, maybe I want to try a bunch of stumps. That's a great idea, we could do it. Minimum number of observations node, let's try 1 and 10. And if it tells me that 10 is the best choice, well, maybe I also want to add 15. You know, I like to see that it's choosing parameters where I've also experimented with values larger than it and smaller than that. And it's honed in on one of the middle one. That's kind of, that's another nice way to navigate these things. So yeah, if I went back and, let's see, so hold this constant at 2, but I'll try, remember minimum observations a node.